Okay, I think we can start. Our speaker is there, and we have with us also presiding professor of today, Professor Vishal Sood. Is already in line. So shall we start?
Yes, I'm ready.
Yeah, okay, fine. So, okay, let me start this foundation week lecture by our today's speaker, Professor Dipankar Banerjee. He's a director from ARIES, Nainital. And we have today's today's foundation lecture with us Professor Vishal Sood, because Professor Honorable Vice Chancellor Professor S.P. Bansal ji could not make it to join this lecture today because he has some administrative work somewhere, so he could not join. So that's why we have Professor Vishal Sood with us, and he is our registrar also of the university. He is dean and head of Department of Education, School of Education. We have connected with us a number of senior professors like Professor Mahajan, Professor Pradeep Kumar, and Professor Shastri, Oske Shastri, and Professor Aluwalia, P.K. Aluwalia, sir. I could see him, he's also joined from Shimla. He's presently president of IAPT, Indian Association of Physics Teachers Association. And I welcome you all, sir. And we have with us all faculty members of the department and of the various schools and departments of the university, heads and deans, students. I welcome you all for this foundation lecture to be organized by the Department of Physics and Astronomical Science. Professor Humchand is the main epicenter of this program which is being organized, and Professor Humchand will be introducing our today's speaker. So before that, I would like to invite Professor Vishal Sood to formally welcome our today's speaker, Professor Dipankar Banerjee. Professor Vishal Sood is an educationalist. And as I said before, he's having presently the charge of a registrar of this university, and he's head of the Department of Education, Dean of School of Education. He's a good researcher and member of various academic bodies all over the country, and he's a member of Department of Advisory Board in Curriculum Studies of NCERT, and well-known researcher and psychometrician and statistical data analyst, Professor Vishal Sood. I request you to please welcome formally our today's speaker and other dignitaries. Professor Vishal Sood, please.
Thank you, Professor Chauhan. At the very outset, a very good afternoon to all the professors, all the teachers, and the research scholars and the students who are here on this virtual platform on this special lecture being organized by Department of Physics and Astronomical Science, Central University of Himachal Pradesh. Very warm welcome to all the dignitaries, the director of ARIES, Professor Dipankar Banerjee. Very warm welcome to all on behalf of Central University of Himachal Pradesh. And congratulations to Professor Humchand, the Dean and the head of the Department of Physics and Astronomical Sciences, and the entire organizing team for organizing this lecture and inviting Professor Dipankar Banerjee, the director from ARIES, to deliver his expert lecture on the theme variability of our nearest star and the sun and its impact on our life. Very warm welcome to all. When I was asked by our Honorable Vice Chancellor that he could not join due to certain preoccupations, then I went through the topic and it attracted me a lot. Although I do not belong purely to the sciences, earlier I was a student of science during my graduation days as a student of BSc non-medical. Then I shifted towards the social sciences. But when it comes to the integration of sciences and social sciences, it's really a beauty. It's really a beauty. And I compared this topic as a social scientist, that is variability of our nearest star and the sun. When we consider social sciences research, there one thing is there that we go for sociometry and sociograms. You have selected this topic with the special reference to astronomical sciences, but I am looking at this topic as a social scientist. We in sociometry, we in sociograms, we have also stars in a particular group of students, and how to identify those stars. There are isolates in those groups. So definitely in any group or in every class, in the group of students, there are some stars who are liked by all, or there are certain students who are not liked by certain students. So groupism is also there in the among the students within a class. So stars and the sun, there is one hero in the institution or in the class also. You can term him or her as sun. So these are the stars and suns from the social scientist aspect. And definitely these stars or sun, what I have heard about that due to those movements of the moon, we see different variations in the sea. So definitely these suns and these stars, they have very much impact on our life. Similarly, the students who are isolates in our class, similarly the students who are the stars of our classroom, they also impact our life. They have much impact on not on the life of the students or their peer group, but they have impact on our life also. So I'm seeing this topic from that point of view as a social scientist. But anyhow, it is a topic that relates to the astronomy, and my best wishes to the whole department from the university side. And my congratulations to the entire organizing team for organizing this lecture and inviting Professor Dipankar Banerjee on the occasion of University Foundation Week celebrations. A very warm welcome to all, and thank you once again for inviting me and for giving me opportunities. Thank you very much, Professor Chauhan. Over to you now.
Okay, thank you, Professor Vishal Sood, and for giving a wonderful social science explanation of sun and stars and the social scientist, the aspect of social science. So now I would not waste any time and would request Professor Humchand, who is currently heading the Department of Physics and Astronomical Science. And he is also Dean of School of Physical and Material Science, to introduce our today's speaker of this Foundation Week lecture, Professor Dipankar Banerjee.
Okay.
Over to you, please.
Thanks, Professor Chance. So, it's really a pleasure for me, basically, to introduce today our, favorite director, Professor Dipankar Banerjee from Aryabhatta Research Institute of Observational Sciences, which was also my Karma Bhumi for almost dozens of years. So, if you ask me that is there any busy, very, very busy person in astronomy, especially in North India, so it's basically Dipankar Banerjee. So if you do WhatsApp chat to him at 12 o'clock in the night, there will be instant reply. I don't know when he sleeps. So I used to wonder actually, with a short time since he joined ARIES in 2019, unfortunately, I have very small, I couldn't work, very small, I didn't have overlap with when Professor Dipankar joined there. So there was complete change in the institute. So that's actually because of this extremely busy and doing multitasking simultaneously. So it's really honor to introduce me today, because I have heard about Dipankar that when Aditya mission was going on, so it was in the peak of his activities. So Dipankar used to be the main driving person behind. So he is the person who used to have Zoom meeting from while he's driving in Bengaluru. So formally, if I just try to introduce you, so Dipankar Banerjee, I just saw it from his website. So he has been master from Kolkata University, and then PhD from Indian Institute of Astrophysics, Bengaluru in 1996. And after 96 to 2000, and this PhD was done on a very complicated subject called magnetohydrodynamics, phenomena of solar atmosphere. So I hope Dipankar will not talk about such a very, very complicated and advanced things today. So he will talk about some simple thing which we can all understand. And from 97 to 2000, he was a postdoctoral fellow at Almar Observatory in United Kingdom. And then he was from 2000 to 2003, he got a Belgium fund for scientific research. It was a center for plasma astrophysics in Belgium. And then 2004 onward, he was a faculty at Indian Institute of Astrophysics, Bangalore, which is the biggest institute of astronomy in India. So, and he was there till 2019, and because in 2019 he moved to Aryabhatta Research Institute of Observational Sciences, ARIES, as a director. So I think there's so many things I will just cut in short. If you see the publication, more than hundreds of publications, more than around 50 PhD students, dozens of DST and SCRB projects as API, and editors of various journals. And more importantly, which is inspirational again, he has a lot of associations, academic associations. The most important one which matter for Indian is the Astronomical Society of India. So everybody know him during when he was a secretary in Astronomical Society of India, how he has completely changed this Astronomical Society and make it completely digitized. And that is also reflected in this one of the wonderful work he has done. He has digitized the Cavalur's solar observations over many, many dozens of years. So all of them are now digitized. So it almost saved the history now. So that was one of the DST project, I think, very big project recently Dipankar has finished. So Dipankar Banerjee is fellow of Indian Academy of Science. And very recently, he was elected unanimously as the president of Astronomical Society of India. And I think today we will hear about what kind of changes, what kind of new excitements are there, because he is also the chairman of this SAC member of 30-meter telescope. So involved in many, many mega projects. So if I try to list all of them, I think I will just eat the precious times that all of you would like to hear. So I think I will just stop my introductions here. That's really, really an exciting opportunity. And we are also fortunate that Dipankar has kind of blessing for our department. For example, Dipankar has first offered that we can hold Astronomical Society meeting at Dharamshala. I couldn't take up that proposal or that offer because of some infrastructure constraints. Hope as soon as we will have have infrastructures here, so we will certainly accept this kind of offer, being he as a president of Astronomical Society in future's time. And also recently, Dipankar has been instrumental in initializing a memorandum of understanding. So he just did it so quickly that it was really an inspirational that we could now sign a memorandum of understanding with ARIES. And also there is a ongoing project. Dipankar is a key member of that committee that we want to install here 1 meter telescope with ISRO, and Dipankar is in that committee, in that high level committee as well. So I hope with this, anyway, there is going to be a lot of talk in future, a lot of collaboration with ARIES. So let's, Dipankar, you start all of them today onwards. So over to you.
Thank you very much, Home, for a very generous welcome. I think the expectations are now too high. I will first of all also thank you, Professor Sood, because he has given me a different perspective of the talk which I was, going to present. But I think it's also a very important aspect which he mentioned about the social sciences and how our our nearest star, the sun, affects our social behavior and history and so on. So without further ado, let me get into my slides. So what I'm going to talk about is variability in the sun, because we think that the sun is there, so it's always emitting the same radiation and it doesn't change, but it is not expected to change substantially, but it does change. And it has some 0.1% of variation of its total energy output. We call it the luminosity of the star. And that change, whether it can affect us at all, or if that change is rather than 0.1%, it is more, then what effect it can have on our behavior and our assets and so on. The other thing is the variability of, when you talk about variability of any object, the time scale of variations are also very important. So there could be variability of the order of seconds, minutes, hours, days, months, years, millennia, and so on. And interestingly, sun does show variability in all these spatial scales. And now you can imagine that the physics behind these variabilities will be all very different in nature. So that is something which I will be trying to impress on today. So first of all, let me show where I am. So this is our campus in Manora Peak, Nainital, and I'm sitting here. This is my window here. And we have plenty of facilities in this particular campus and another campus, which I will talk about as I move on. So what I plan to do is the major part of my first half of a little more than a half of my talk will be on the nearest star, the sun. And then I will talk about some of the facilities, what we have, and how we can utilize some of these facilities with the joint collaborations and work, visits of students and faculties. There is another aspect which is very important in today's modern day astronomy, is the nature of the multiple wavelength. As we know, most of the objects in the sky, they are very high temperature and often high density and so on. And they do emit in all possible wavelengths, from short wavelength as X-rays, gamma rays, to UV, to infrared and visible, and the longer wavelengths. Unfortunately, from the ground, if you restrict your observation, which has been the case in the history, the observations have been limited to the, mostly in the visible wavelength. So if I look at the sun in a visible wavelength, some days the sun will look like a flat, just a bright white light circle. It doesn't show that much of variations or that much of structures and so on. But now if I look at the same sun in different wavelengths, namely if I go to a little high in the mountains, we start seeing infrared. And infrared sun looks something like this. If you come to the Devasthal, which is our other observatory, we are planning to have infrared observations for sun as well in future. But of course, right now we have infrared observations from other galactic sources. Now, if I go to space and start looking with the ultraviolet or extreme ultraviolet wavelengths and look at the sun does show many more structures and features and so on. It is actually the same time image of the sun taken in this different wavelength. And then if I go farther up, and look at it through an X-ray telescope, again, it shows very, very different structure. So you can imagine that sun does show plenty of structures on the surface and in the atmosphere. And those structures are, now we will see as I move on, that the structures are all controlled by the presence of the magnetic field. So magnetic field plays a crucial role in formation of these structures, their evolution, their growth and decay, and eventually if there are certain explosions in the sun and so on, what we call flares or coronal mass ejection, they're all controlled by the changes in the variability of the magnetic field. Since I am talking about variability, all these variabilities are driven by magnetic field. And I think whom was mentioning, I assure you, I will not show you the mixed equations. So that's the reason actually, just the pure hydrodynamic equations are not enough to explain the physics behind these variability. So one needs to invoke magnetohydrodynamics. It's basically one end of plasma physics, which we invoke. So for physics students and all that, if people are interested, I can talk about it much later. So as I mentioned, the variability of different time scales on the sun, like all stars, is a very dynamic star, always active, always changing. More we learn about it, the more we learn about all stars. The point is that sun is our closest star, and the amount of details what we can study about sun is actually not possible for other stars, because the most of the other stars, we study them almost like a point object. Here is a star where we can really see the detailed structure on the atmosphere, and there are ways now even to look at the interior of a star by different techniques of seismology and so on. So here I'm showing you a movie taken from, again, a NASA satellite called Solar Dynamic Observatory, which is looking at the atmosphere of the sun. And here you see there are regions on the sun where things are very bright, and there are these structures. They after a certain time they become unstable, and there is a huge explosion. Lots of material is thrown into the interplanetary space. Some material falls back into the sun. When the material falls back, then again it interacts with the lower atmosphere and can give you again a huge explosion or some other radiations and heating and so on. But now the point is, when you saw these kind of explosions, these amount of material, if it travels through interplanetary space and comes towards Earth, we could be in trouble. It does come towards Earth, but fortunately, Earth had its own magnetic field. So the magnetic field provides us a shield, and it protects us from all these material which is coming. Having said that, the magnetic field protection is only limited to certain height in the atmosphere of the Earth. These are called the magnetosphere of Earth. If I now have a satellite which is beyond this magnetosphere, this is completely in an open field. So this satellite is getting bombarded with this kind of material which is coming from the sun, and these materials are highly energetic with high energetic particles, magnetic field content, and so on. So very regularly, actually, lots of satellites are getting damaged, and there are other assets. Of course, people are talking about space tourism, space rock. So all these are going to be badly affected unless we are able to know when such an explosion is going to happen in the sun, and if it happens, then how to protect our assets in the space. So that's an area called space weather, and I will talk about that a little while now. Now, in terms of the physics, our sun provides an ideal laboratory for plasma physics, atomic physics, particle physics, nuclear physics, you name it, because whom mentioned, I came actually from a purely theoretical physics background, master's with the condensed matter physics from University of Calcutta. When I went to Indian Institute of Science for this astronomy program, I had no clue about what stellar astrophysics or astrophysics in general we could do. And then I realized after this very rigorous coursework that there are different branches of physics which you can utilize here for your understanding of the physical principles which are behind all these dynamic behavior. So that way, sorry, I will just try to unmute somebody. There is some little noise. Yeah, I will request you to do that.
I have done that. I have done that.
Okay, thank you. Yeah. So for physics students, again, if you have any questions post the meeting and all that, you name any of branch of this physics, I can give you hundreds of examples where, you know, astrophysical applications are there, and sun ideally provides that laboratory, because in the laboratory environment, you cannot achieve those conditions which we can achieve in the astrophysical context. That's why, you know, astrophysics has become a good laboratory for sun. Now, the other question, probably I will just go back one more time to the previous slide. This particular region where the intensities are very bright, and there were all these kind of magnetic structures. And if you see these magnetic structures, they are formed in terms of a closed structure. So we call them coronal loops. So there are different atmospheric layers of the sun. The visible surface is called the photosphere, and then we go to the atmosphere called chromosphere, about 1,000 kilometers above the photosphere, and then the extended surface, atmosphere of the sun is called the corona. In fact, the coronavirus has been named from an eclipse image of the solar corona only. Not many people are aware of this fact, because during the total solar eclipse, you have these kind of, you know, helmet kind of structures, and when the virus was seen first time in the microscope, they felt, oh, are we seeing a total solar eclipse or what? So they named it as a coronavirus. Okay, that's a side story. So let me get back again to the fact that there are regions in the sun where there are strong, you know, intense region. These are called active regions. And now we understand all these active regions are governed by presence of strong magnetic field. There are regions away from these bright regions where comparatively things are darker. Traditionally, it used to be called as quiet region, because the observations, you know, maybe 30, 40 years back, of course, was not there in the space era. People did not have regular observations of these kind of dark regions, and they felt that, you know, there are not much of dynamics happening. So that way they can be called as a quiet region. But be aware now, it is a completely misnomer that nothing is actually quiet in the sun. It just, if you compare, these regions are more dynamic. The time variability is more important here. Here also there are lots of different kind of time scale changes, spatial changes. I will show you some movies on that as well. So here again, these regions are called active regions because underneath there is strong magnetic field. These are kind of magnetic structures. So this is a photospheric picture. You see these are called sunspots. Sunspots are regions where strong magnetic fields are there and sun rotates about its own axis. What I am trying to again portray here is the aspect of the multi-wavelength astronomy. So it is so important that we look at the sun in multiple wavelengths, because this is one wavelength which is in the visible domain, and then we have two different ultraviolet domain, which is allowing us to look at a very higher up in the atmosphere, about 2,000 kilometers. This is about 1,000 kilometers and so on. And if you look at different layers of the atmosphere of the sun, you start seeing actually much more different structures, but they're all actually connected, because they're like a building blocks. You know, you have a pillar which is anchored in the surface, but the pillar may change its shape as it goes into the higher up in the atmosphere. So that's a overall view of the sun in the active region. Now that's a closer look. Now what I am showing here is, this is an image, a lower edge of the sun. This is called a lower corona. Image is taken from imaging instrument. But now if you really want to see the outermost atmosphere of the sun, you have to block the solar disk and then see the extended part of the corona. This is exactly what happens in the total solar eclipse time. If you have seen a total solar eclipse, please note that the moon blocks the solar disk light. And during that time, the faint emission which comes from the corona, actually the emission coming from the corona is 10 to the power minus 6 times. It's a 1/1,000,000th time, intense than the full disk image. So you can imagine, unless you block the solar disk, you will not see the extended part of the corona. So that's why these artificial total eclipse situation which we create from the space are called coronagraph. So these coronagraph allows us to, track anything happening from the sun, all the way from the sun to the earth. So here actually I am now combining data from, these are actually two different coronagraph. Then these are called heliospheric image. Heliosphere means the sun, planet, the entire system is called heliophysics. So now we are not actually studying the planets, the Earth atmosphere or the star atmosphere separately, because now we understand that this works as a coupled system. As you can see, if anything change is happening in the sun, it does travel through the interplanetary medium, and then it's interacting with the planets. And particularly if in the Earth's environment, we do have to worry about what's going to happen. If you are moving around here, I'm sure you will not like to be bombarded by this kind of highly concentrated mass charged particles. Note it, if these are all plasma blobs of temperatures of millions of Kelvin and so on and so forth. So it's not really very pleasant material or a mud which is thrown at you. I was talking about the active region, and I mentioned that even in the quiet region, so-called quiet region, how much dynamics you see. Here I'm just showing you a multi-wavelength observation of the quiet sun. This is data combined from Big Bear Solar Observatory in US and the Solar Observatory, which is in the space from NASA. Now, why I'm showing this is, again, showing you the multi-wavelength nature. Multi-wavelength observation is allowing us to map the different layers of the sun. This was led by, again, my former PhD student who was in the US. He has come back to India now, has joined as a faculty in Institute of Astrophysics a few months back. But the point is, this is the way, if you combine, work from the ground and the space, and if you have a very big team of workers, if you notice here, there are people from India, from Russia, from Europe and US, part of this work. Of course, that led to a paper in Science. So that demands actually the expertise from different places. And what is showing here is that there are dynamical changes. This is the magnetic field which is changing here. I think I have to go back to play this movie again. Here, so you see these are again concentrations of magnetic field, and magnetic field always comes in pairs. The blue and the red shows opposite magnetic polarities. And when these opposite magnetic polarities come closer to each other, they interact with each other and then they produce jets. So these are jets produced by a process called magnetic reconnection. Again, these are MHD processes. I will not go into detail, but these magnetic energy then get converted into kinetic energy and heat. So these jets, which are formed because of the magnetic cancellation process, they travel all the way. This is a map in the chromosphere, and then all the way in the corona, you see these jets will carry this energy, and you see often brightening here. Brightening means there is presence of a heating, localized heating in the upper layers of the atmosphere. Then this particular thing has been originated from the much below in the photosphere. Why these also effects are important is, I didn't mention that there is an outstanding problem in the sun. The corona, which is the outermost layer of the sun, is actually much hotter than the surface of the sun, which is a big surprise, right? I mean, if in the Earth's atmosphere, if you look at from Delhi, if you come up to the mountain, you expect the temperature to go down because the sources are all in the ground. So in the case of the sun, this is completely opposite. The surface temperature is about 6,000 degree Kelvin. And as we go to the chromospheric height, it is 10,000, 20,000 Kelvin, and then all the way into the corona, it is millions of Kelvin. This was completely, a puzzle 20 years back, but now do we understand from these kind of observations that there are these processes which are carrying the energy from lower height to the upper height, and also this energy is generated because of non-thermodynamic process. The normal thermodynamics will not be able to explain this, but non-thermal processes is responsible for this heating of the upper layers of the atmosphere of the sun. There is again another element which I will talk about is, this is an image, a total solar eclipse of the sun taken around 2006. This is 2008 image, 2009 image, and 2010 image, taken with two different filters. Again, as I mentioned, two different filters correspond to two different temperature, plasma. And here, if I overlap the two different images, I often do not see perfect overlap. So that also proves that there are certain structure which are of certain temperature, and then a certain other structure which are of different temperature. So that means the most of the plasma structures which you see in the sun is actually multi-thermal. Incidentally, if you look at these images, probably you can mimic the coronavirus, in some sense. But the other interesting aspect, if I now compare from a 2006 image to 2010 image, that how the structures have evolved, and you see much more structures in the 2010 as compared to 2006. So that means sun does vary over a period of years as well. What I was showing you in the earlier slides were mostly changes which were happening in terms of, minutes to hours time scale. But here you see a time scale of change of, of several years and so on. So both kind of variability we have to worry about. So do we understand the global field of the sun? This is again a mystery, because the magnetic field measurement is actually quite a tricky thing. Magnetic field is measured again through normal Zeeman effect, spectral line splitting, and these Zeeman splittings are very, very limited to certain spectral lines which are formed in the lower atmosphere of the sun. We still do not have a regular observations of the coronal field measurement. So this is again another area where theory is only our source at this point of time. But of course, the theoreticians are smart. Combination of mathematical modeling and computer simulations are giving us a picture what you could expect from a magnetic object of this size. So here I'm showing you a magnetic structure of the corona on a large scale, and this was a prediction from from my colleagues in the Center for Space Science says at CESI Kolkata. I'm actually associate faculty in that center as well. So they produced this kind of global coronal map before the eclipse day. So this eclipse only shows you this extended part of the corona. Of course, you can go to the space and see the coronagraph, but there are certain limitations of what kind of details you can see from the space-based coronagraph. Eclipse provide you the perfect eclipse, perfect coronagraph for that matter, because moon absolutely fits the sort of solar disk size, and we are devoid of scattering and so on, because this particular blocker is much away from the earth and so on. So now these kind of theoretical models which are giving us this kind of global magnetic structure is quite an important issue. Who mentioned about Aditya mission, and with the Aditya mission we expect to do certain observations for the first time from space, which can be compared with these theoretical models and so on, to get an understanding of the global field of the sun. So that's our Aditya mission, which is a multi-institutional effort, and we are in the final stages because of the pandemic. Some of the assembly and the delivery of components and all that was really hampered very badly, and now we expect that this sometime very soon we'll be delivering, and hopefully if this year, or if not this year, early next year we'll be in space. We are going to a different location called Lagrangian 1 point. This is 127,000 kilometers away from the Earth. And it's a very good vantage point to continuously look at the sun. The other thing which I will be very briefly talking about are the sunspots, which are the magnetic structures. So now we understand that all the dynamics, all the changes what we are seeing is because of the presence of these magnetic concentrated regions. They're called sunspots. These sunspots are anchored deep inside the sun, and you can visualize them as this kind of magnetic structure, magnetic field lines. And when these kind of magnetic field lines, if you are actually twisting them and turning them and so on, beyond certain terms and so on, you will find that this magnetic field structures will actually erupt, and then you will get a ejecta out of that. But now these sunspots provide us a clue about the presence of the magnetic field. Does this magnetic field change in a very long-term scale also? I'm going to give a little story about this last 400 years of sun, because as I indicated, it is important for us to know that whether sun was the same 400 years back, and if we see certain changes, is it going to change drastically in next say decades or 2 decades or 100 years, so that our existence or our climate can be heavily influenced. Professor Schuth talked about social sciences. It will also have a direct impact on our social sciences. You think about a situation, we are all in this part of the world, we like, sun so much. Suppose, several months or several, or even a year, the sun is not bright. I mean, it's all cloudy. What effects it makes to our temperaments, our mood? These has a huge impact. So it is important for us to understand whether this emission from the sun is going to vary or not. What is shown here in this particular plot is the sunspot number. If you look at the sun in one day, you may find 1 or 2 sunspots in some day. Some days you will find 10 sunspots. Some day you may not find any sunspot at all. So is there any periodic pattern? What is plotted here is a sunspot number for last 400 years. Very clearly, we see a kind of periodicity, which looks like, sometime there are, lots of sunspots in the sun, and there are certain period where there are hardly any sunspots. And this has a periodicity about 11 years, not perfectly at 11 years, but you see the amplitude of these things. Certain times, certain 11-year period seems to be much, more active than the other period. Now, if we look back to the history, of course, the older history, there are always challenges or kind of, question marks about the observation, their qualities and all that. But if you look back at the older history, it appears that between 1650 and 1700, there are hardly any sunspots for 50 years. And what was the impact of that? The Volga River in Europe was frozen for 40 years. There were several tens of thousands of people died of extreme cold weather in Europe. I don't think we can afford this kind of changes in today's modern world. And so it is important for us to know what did happen in the sun, that there were hardly any sunspots. We do have some physical understanding about the sunspot in terms of a dynamo theory. I don't have time to go through that. Some of us work on this in detail, but whom mentioned about this data archive, because from Kodaikanal, we have been looking at the sun for last more than 100 years. Actually, he talked about some decades. Actually, it is more than 100 plus years. So this is a perfect image. Any day, you will now go back to the archive and look at 1st January 1958, image in H alpha, calcium K and white light. The other beauty of this particular data archive is that sun has been looked at it in multiple wavelengths. You don't find it in anywhere else actually almost in the world where all these 3 wavelength images are available. So we have now worked on this and we have created this complete database. Calcium K data is available from this more than 100 years. White light 1904 till date, we still work, observe for a very small telescope with an X-ray, plate these images to make this consistency. H alpha and prominences. So this is all available in the public domain, and I'm very happy that every other week I see a new publication coming from other parts of the globe, and I'm not in northern list at all. So this is, I would say, my satisfaction that this is really becoming a global resource for doing top quality science. This is a work done by my former student who is now in Max Planck, and they've worked on data from 13 data sources across the globe, and they cross-calibrated this sunspot area. So now we're trying to get an estimate about the magnetic field in the sun over, say, last 100 years, because observations are only there for last 100 years or so of this kind of level. Sunspot number data exists for certainly longer, but sunspot area provides us a little better measure about the flux of the magnetic field in the sun. And you clearly see that all these, solar cycle behavior here. There is another aspect which I won't be able to talk about at length. These sunspots in the beginning of the cycle, they actually appear in the higher latitude. And with the progression of the solar cycle, they move to the equator. And if you plot these location of the sunspots over last, decade and so, you will get this kind of beautiful image, which is called the butterfly diagram, because they're living beautifully the butterfly nature. And this is again the state-of-the-art sunspot area catalog done by my student, including data from 13 different observatories across the globe. So this is going to be the landmark or reference. So the future of solar physics is actually with the youngsters. This is my My student gang, we had a school, a couple of years back in Leh. Of course, I'm fortunate enough to go for different solar eclipse expeditions as well. This was the one last I could go into Argentina. This is all about the sun I wanted to talk about. Now, rest of my 10-15 minutes, I will spend about the facilities at ARIES, and introduction, very, very short introduction about the Aditya mission again. So ARIES is an autonomous institute under DST. We promote, guide, and carry out frontline basic research in the area of astronomy, astrophysics, and atmospheric sciences. This is again another element not many people know about ARIES, that ARIES has a good atmospheric science, lower atmospheric stratosphere, troposphere, observations, and I will talk about it a little more here. ARIES operates India's largest optical telescope at Devasthal at 2.5 meters. This is the state of the art and nation's pride, I would say. And also, India's highest altitude aerosol observatory. So, although ARIES is a small institute, but it's proud owner of these two, major facilities in India. This is our Manora Peak campus, where I am in this particular building here. And we have the new campus at Devasthal, which is in Mukteshwar, 50 kilometers east of Nainital city. This is a close-up of, again, our campus here. We have some more telescopes here. These are old telescopes, but very good working telescope. This telescope will celebrate its 50-year celebration very soon in this year. And then we have other lab facilities. Of course, the students are here. The electronics and optics lab, and the guest house and so on. So please feel free to visit at some time. This is the 1 meter telescope which I was talking about. Really, really active for last 50 years. Our students, just after dinner, they walk to this telescope to do their observations, and which has led to many, many PhDs. We also have a solar, observing facility with the H-alpha filter. We look at the flares on the sun. It's a modest facility. Combining with the space observations, you can do reasonable science. We also have a 1.3 meter Devasthal optical telescope in operation since 2010. In fact, I understand Home was the most active user of this telescope probably during his time here. More recently, we got this 3.6 meter Devasthal optical telescope, which is the nation's pride. We are also, just in the process of commissioning a 4 meter liquid mirror telescope. This is a unique concept. Rather than using a mirror as a reflecting surface for the telescope, if you can use the mercury, mercury is a liquid, but it is a very good reflector as well. So if you can pour mercury in a big bowl and then rotate the mercury, it can take a shape of a paraboloid, and then that becomes a very good reflecting mirror, as M1 in the case of a Cassegrain type mirror in big telescope. In fact, I must point out, I think Home was the PI of this telescope before he left ARIES, and before I could join. Otherwise, probably I would have not allowed him to leave this place. So this is the 1.3 meter telescope which I was talking about, and most of the interest which Home has in terms of the gamma ray burst and the AGN studies, supernovae, different variables, transients are all studied from this beautiful setup. You could see the beautiful Himalayan range. It's a pleasure actually to be there and enjoy the Himalayan range along with your observation. This is the 4 meter liquid telescope, which will look at very deep in the sky for distant quasars and supernovae. Unfortunately, because of the pandemic, we couldn't commission it. There is a collaboration between the Belgians, the Canadians, and Indian collaborations as a result of this. So we are waiting for the Belgian colleagues to come, and hopefully any time in next 3 months or so, once this situation improves, we'll be able to commission this, and we'll be hearing more about it. This is the Devasthal optical telescope, the biggest telescope in the country at this point of time. This is the telescope structure inside the dome. Very briefly, I will talk about atmospheric sciences, air pollution and climate change studies, trace gases, aerosols, meteorology, dynamics. So people here, they do take local observations as well with the facilities like from the radar and LIDAR and so on, but they also combine the data from space. We also have balloon-borne experiments. Every week almost we run a balloon, and that particular experiment is combined with the space data for calibration and also for ST radar uses for comparison as well. Since January 2002, all these different measurement labs are there. In fact, we are extending these observations not only from Manora Peak here at Nainital, but we want to do it at Devasthal as well. So there are some new facilities, new labs are being set up at Devasthal as well. As I mentioned, the balloon-borne ozone experiment, you have all these, methane and carbon monoxide and other greenhouse gases, their measurements from multiple sites. Now, the idea is that you have to do these kind of, measurements at different heights in the Himalayas. We have started observing from Devasthal also. We have a small transit campus in Devasthal, not in Devasthal, from Haldwani, sorry. So Haldwani also we have some observations. At Nainital we have some observations, and then at Devasthal also we are setting up some labs as well. So at different altitudes, if you can make these observations, and the comparisons are really, really good for modeling purpose. So that's all I wanted to talk about ARIES. And I think, thank you for your attention. I'll be happy to take up questions now.
Yeah, okay. Thank you, Professor Banerjee, for enlightening us about the sun and its environment, and also about the facilities that ARIES is having in astronomy, and which probably our future MOU, through MOU, our students can also get the facility available for them.
Absolutely.
So I would request the students, or I would we invite students to have some question. If they have any question, please.
There is one question in the chat box. Should I just try to?
Yeah, sure. Please.
Dipankar, if you want, I can read it for you.
No, I've opened the chat box. No problem.
Yeah.
So Vipul is asking, what is the role of magnetic field in all this? So as I mentioned, I think he asked this question when I was showing all these, huge dynamic changes in the happening. So magnetic field plays the crucial role in controlling all the dynamics actually, because the plasma is confined because of the presence of the magnetic field to start with. So the magnetic field doesn't allow the plasma to move in anywhere, because they provide certain kind of channels and certain kind of structures. So you saw those images where I will try to bring back some of the images which I showed. Even this movie, if you recall here. So these are called magnetic loop structures, and they are because of the presence of the magnetic field here. And when this magnetic field is changing and the structure is changing, whatever material was inside, they are actually thrown outside. I mean, in the interplanetary space. Now, the movement of the, all these charged particles in the interplanetary space is also because of, somewhat dictated by the magnetic field, because it is not moving absolutely in the free space, because magnetic field is there everywhere. And as I showed you, even in this coronal structure, if you see here, all these structures are because of the presence of magnetic field. They're much weaker than the strongest in the sunspot, but nonetheless, they are there. And since magnetic field is there, it is basically dictating what would be the shape of these kind of structure. These are snapshots, but if you have an explosion here and material is thrown out, so they will interact with these magnetic, background magnetic field, so to say, and that will dictate finally what would be the trajectory of these coronal mass ejections and so on. So in a nutshell, see, the magnetic field actually controls everything almost in the sun in terms of the dynamics here. There are other changes, of course, happening inside the sun. There are other effects, but in terms of mostly the atmospheric changes, what you see, and the dynamics, the time scales, what you're talking about, are controlled by the magnetic field. Then there's a question by Oyon Chatterjee: how much is the average current near the surface during a solar burst? Okay, it's a very good question. So we are, I mean, rather I have been talking about mostly magnetic field, because it is much harder to measure the electric field. But you're right, whenever there is such a, magnetic interactions and all that, what is produced actually are currents. And these, currents are of very, very high magnitude here. So we are talking about megajoule and so on. I mean, we are fortunate enough that we are away from the sun and at appropriate distance. So these energetics which we are talking about is so enormous that it can actually supply a lot of energy if you can really convert that to other form and so on. So you're right. So huge amount of currents are generated during this solar burst. Rahul Singh is asking what could be the cause of these concentrated magnetic fields on the sun surface or sunspots? Okay. Again, it's a very good question. I did not talk about it much at all. Now, solar-like stars inside the sun, they are convective. In the sense, there are different layers in the interior of sun also. Just 30% underneath the sun is convective. Now, when you have a convection, and as I mentioned that if it is a pure hydrodynamic scenario, things are different. But when the star was formed, when the sun was formed, it formed because of the compression from the interstellar medium. And within the interstellar medium, there is actually a small magnetic field, the micro Gauss kind of magnetic field. Now, these very light medium, if you now go on compressing, so one can show by the order of magnitude estimates and all that, that will actually amplify the magnetic field. And that becomes a seed field inside the star. Now the question is, this seed field has to sustain. Normally, if you change, if you have a current, then only it produces a magnetic field. Other way of looking at it, right? You switch off the current, your magnetic field is gone. So magnetic field decays very fast. So that means you need to have a mechanism which will sustain this magnetic field. So inside the sun, it is believed that this convective process, along with this, motions and all that, is responsible for the generation of the magnetic field. And this process is explained in terms of a dynamo theory. Now, there are other details also, of course. Sun is also a rotating star, and it rotates not uniformly, it rotates also differentially. That means, the equator rotates much faster than the pole. You think about a scenario where, my body, my tummy is rotated at a speed and my head is rotating in a different speed. So what kind of twist and shear forces will be actually applied to my body? This is what is happening inside the sun. So if you have certain magnetic field lines inside the sun, because of this differential rotation, these magnetic field lines are getting twisted and sheared and so on. And that is responsible for the production of the sunspots at the surface. So these magnetic fields, which are there interior of the sunspot, they're like rubber tubes also. Now, if you take a rubber tube and pour it in a bucket of water, what happens? The rubber tube tries to float on the surface, right? This is called buoyancy. Exactly the same thing happens in the case of the sun. These magnetic tubes, they are actually lighter than the surrounding because there is a magnetic additional pressure inside the tube, and they are called magnetically buoyant. So these magnetic tubes, which are generated inside the sun, they come to the surface, and when they pop up out of the surface, they generate the sunspot. So this is what is actually somewhat shown in this particular image. These are these magnetic tubes which has been generated underneath the surface. They float up here. There was actually animation which is not for some reason playing here, and that basically produces this kind of coronal loop structure. And then if you twist these loops further, then you will have this solar burst and so on. So I hope I could answer.
Okay, so if these are all, so I'm also happy to get reminded myself because I was also when I was a student of PhD and then postdoc, I did all this solar neutrinos and magnetic field. We have developed a number of profiles for radiation zone, convective zone, and this and that. So that's and we did lots of models for that and data fits. So it was really reminding for me also for for this thing. And so, am I audible? Hello.
Yeah, audible,
Yeah.
audible.
Okay,
Yeah.
so anyway, this is it was really a nice talk for all of us.
I think,
and
sir, there is many question more left on the chat box.
okay, please.
So Dipankar, there is some question left on the chat box still?
I think Dipankar is.
Oh, I'm sorry.
Yeah. Okay. Yeah, please. There are some questions. I think.
Right.
Questions.
I'm checking it.
Yeah.
So, yeah. Sorry about that. I think it came up. So I think Ritisha's question was about 11-year period of the sun. So I was just going to say that I very briefly talked about that the sunspot number does vary with time. And if I could again just probably quickly share my screen again and go back to that plot. Yeah, so this is what is called a solar cycle. I hope you are able to see the screen. Yeah. So this is what is plotted here is the sunspot number against last 400 years, and the sunspot number varies with time, and this periodicity is typically 11 years. Now there are many more things related to this solar cycle that, as I mentioned, that amplitudes are not always the same. You see there are certain solar cycle which is much stronger than the other one. In fact, the last 100 years, the most updated solar cycle behavior is seen here from my student work. And as you will see here, and the cycle numbers are also depicted here, cycle number 12, 13, 14, 15, 16, they were more or less comparable, but then you saw 17, 18, 19, much stronger. You have many more sunspots, and correspondingly the sunspot area was much higher. But again, 1950s, that cycle was the strongest. We are actually going into weaker and weaker solar cycle. And I did not, again, elaborate too much on this. So this period, which was discovered by Maunder, where sunspot numbers were not recorded at all, and the effect was, very extreme cold weather in the Earth, we still do not understand what really happened. I mean, so this 11-year cycle is explained in terms of a dynamo theory. So dynamo theory is like, you ride your bicycle, your light comes up. So if you stop cycling, your light will turn off. So was it, somebody switched off that, dynamo inside the sun, that, your sunspot? And if so, then why it is again started? So we still do not understand completely. There are certain new work which is now indicating that probably sunspots were there, but the sunspots were probably very weak or very small. And in those years, 300 years back, we have very small telescope and so on. Probably they were not able to detect them. So it was undercounted. So that is one theory and proposal. And there are now explanations also from the dynamo theory, how it is possible to have small sunspots, if you have changed certain parameters of, suppose, your rotation profile, what I was talking about, is changed and so on. So that's how, okay. Then there is a question about ancient Indian astrology centers around the sun. How do we relate to it as a scientist? I will probably avoid this question because, we are professional astronomers, and, I'm really, you'd like to stick to, sort of, scientific explanations in terms of physical explanation. people have their own beliefs, but personally, I don't have much comment about astrology. Harshing said probably this is out of the topic discussion today, but I want to ask about field of astrobiology and what is the future in India. Okay, it's a very new emerging field. Yeah, I did not talk about astrobiology at all, but in fact, we hosted a workshop which got over today. Yesterday, we had a half-a-day session on astrobiology. We are also was actually discussing about radiation and the effect of radiation, solar radiation and extragalactic, cosmic rays and so on and so forth. That effect on, on biological species or biological molecules, so to say. Astrobiology, there are certain people working in some institutions in TIFR, some are in IAA and so on, but it's an emerging field. And yeah, it's a new field, I would say. I can't really comment how much, future is there because it's a new field. I'm sure if people from, different context chip in, because this is, again, this is one field where you would need multidisciplinary approach as well. You need to know biology to a certain level to understand, but at the same time, you need to know the astrophysical context or, the environment where you have to, study this biology. Yeah, I don't see any other questions in the chat box. Yeah.
Okay, Dipankar, I have one question.
Sure.
This dynamo theory, solar dynamo, is all about the the some dynamo is there at the convective zone at 30% deep in the sun.
Exactly.
And is there anything else like or people are also, I think, because I'm also involved in that this through neutrinos, we are probing inside the sun.
Right.
So what about, is there any theory about the radiation, any kind of dynamo at the radiation zone or any magnetic field source at the radiation zone or of the sun?
Yeah, it's a very good point. So there are alternate concepts of of having magnetic field in the core even, but from our current understanding of the convection theory and the tachocline, tachocline is the interface between the radiative zone and the convection zone, and there are actually there is a field called helioseismology, which looking at the the oscillations of the surface of the sun, you try to interpret the interior structures and so on. From the helioseismology results also from line splitting, all there now indications that at the tachocline convection zone probably there are presence of magnetic field, which causes the certain order and even order separations of the spectral lines. So there are now more support coming in terms of observational evidence of strong magnetic field of the order of almost megagauss in the base of the convection zone, which eventually when it comes to the surface will be kilogauss strength. So that is what is expected and all that. So that theory seems to be standing now. There are some global MHD simulations which are coming now, which also are sort of giving some indications about magnetic field generation inside the sun, but much deeper. There are alternative theories, I will put it that way, but not so popular. Yeah.
Right. So there are any other probes like neutrinos? People are they also they are also probing inside, or any other kind of other probes are there also currently or working on it?
Yeah. So as you rightly pointed out, this solar neutrino problem was a problem for many decades, and in fact, it's
my PhD thesis was on that. Yeah.
Wow. So there was a tussle between the particle physicist and the solar physics community. Who is wrong?
Yeah.
Who is wrong? The solar physicists, they were asked to change the temperature inside the sun by a small amount so that the reaction rates can be changed.
Solar models, yeah. There are various solar models.
Right. So solar neutrino problem again is a classic, and as you rightly pointed out, it's again a very good example how particle physics, and the stellar physics community in general, and the solar physics, of course, the experiments in terms of chlorine experiment, the Cherenkov detector, Sudbury Neutrino Observatory. I mean, you name it. So it's again really showcase of these multidisciplinary nature of physics and astrophysics, along with the technological advancement, on the detection levels and all that. So so I do not know in any other particular solar neutrino experiments are continuing in the solar context, because solar neutrino problem is solved, so to say. But whether neutrinos are used as a probe for other experiments as well, that is true. That is still some of the nuclear reactions and all that, because I mean the energies which you get from different flavors and what energy range you have can give you refinements of your nuclear reaction rates, and because it's primarily the PP chain, but you have a CNO cycle also, which will contribute to a few percentage of the energy generation. So these kind of refinements, I think it's still going on. It's not my field, but I understand it still goes to some extent. Yeah.
Okay, fine, thank you. So anyway, if there is not any question, so let me thank Professor Dipankar Banerjee formally.
Sir, there is 2 questions, I think.
Oh, I see. Okay, fine.
So, if we have time, I don't know whether we have time.
Yeah, I'm fine.
Sure. Maybe if Dipankar is. Yeah.
So last question I see, Ritesh Bharadwaj. Sir, how do they really observe sunspot during 17th century? Okay. So Ritesh, already Galileo started looking at the sun from Newtonian telescope. But those days, of course, there is a myth that Galileo lost his eyesight because he was looking at the sun through the telescope. That's not correct, actually. It's not a right story. They were always, looking at the reflected image. So you hold a white sheet of paper, and then you see the projection of the sun, and there sunspots you will be able to see. In fact, Galileo had a hand drawing of sunspots. And from those hand drawings, people could even compare, next day's, drawing and so on and so forth. In fact, Galileo also mentioned that sun is rotating around its own axis. He didn't know sun was rotating differentially, but he did discover that sun was also rotating. So that's 1600. Okay, so much before even what we are talking about, this Maunder minimum. So sunspot observation, Chinese were doing meticulously as well. But as I said, if you have a 4-inch telescope, there will be certain limitations of the resolution and the size of the sun what you have. So if you have a very tiny sunspot, you may or may not see it on a projected image plane. So that was, I think, one possibility, that there were sunspots, but they were not seen because of the limitations in the observation.
Dipankar, there's a question from Neha Katoch. Sir, what was the observational evidence historically about a nuclear fusion scenario of solar energy?
Observational evidence historically about nuclear fusion scenario of solar energy. Of course, the first experimental thing was the chlorine detector. This was in it was Davis. In fact, you just heard from Professor that he was the expert in this solar neutrino experiment. So this was done in the mine.
60s.
Yeah. So
60s,
70s. It was even 37 or something where it started. And the Davis's results started coming in 60s. So so people knew, of course, the energy source of any star is through a thermonuclear reaction was known for many years, and then it was expected that in that proton-proton interaction you will have neutrinos. So people were started looking at the neutrinos, and they went down in the mine. And then there were huge chlorine detectors were built. Davis, eventually Davis got the Nobel Prize when the solar neutrino problem was solved. So those things happened in almost 100 years. Well, about 18, 19 years back already started. Is that all? Or yeah, I mean, I've not opened the chat box again. As an astronomer, what are your comments about the WOW signal? Again, there are research going on. So I do not really know the evidences yet. So I will leave it for discovery to really confirm this.
Okay, so I think we should conclude now. And I formally thank Professor Dipankar Banerjee for giving us such an enlightening talk on the importance of sun and the environment of sun, or also the social aspect of sun. It was very enlightening for all of us, and mostly about the magnetic field of sun, and also the shield of earth magnetic field, which is very important for life to exist. Had it not been there, then definitely life would have been totally completely finished by the solar flares or the solar or any other radiations. So this was very interesting, enlightening, and also the facilities he talked about at ARIES. And definitely our students will be going to be benefited from that. And we hope that in future he will be having a live session of Dipankar here in CUHP in future, in very near in future, once this corona, this pandemic finished of its trial. And this is all. And I also thank all the professors and students and Professor Humchand for organizing this wonderful talk. So thank you, Dipankar, and thank you all. And thanks all. Let's hope to meet you soon physically. Thank you.
Sure. My pleasure. I'm looking forward to visiting you. Yeah, thank you.
Okay, sure.
Thanks a lot, Dipankar. Excellent. Wonderful.
Okay. Bye-bye then.
Bye.
I'll just end the session then. Yes.
Bye.